we may just start with the first introduction slides. Just repeating a little bit to give the general base. That was our general colorful introduction slide. Just a reminder, we have the InChI, the core InChI, as the main description for a structurally represented molecule. And the reason why I'm saying it that carefully will come out a little bit later. The InChI as such, we have got around the InChI key that is developed out of that one. And then we have a bunch of applications that use the InChI. And the ones we talked about, that one were the reaction InChI. And today we are talking about the MInChI InChI. If you just go to the next slide, please. Those are the different working groups we already mentioned a few times. And now on the next slide, please, you just see we're just on the working group MInChIs that is headed by and chaired by Leah. Just one more aside from my side. We just had this very general introduction about InChI as an identifier, and just as a very short, well, reintroduction, have in mind it's an identifier. It's not the full chemical representation. You see on the left the two nitro groups. Actually, that nitro group that is less preferred as the InChI is based on the InChI representation. And out of a bunch of other rules, but it makes it easier to represent it like that as an identifier. And on the right side, you see the different levels, and layers the InChI is set up. Yeah, so you've got the version number, of course, you got the chemical formula, you got the connectivity, and you got the hydrogen layers. So have in mind, InChI is vice versa. It does not describe bonds, it describes all the ligands you have, and then from there you have to recalculate bonds. And with that, just a short comment before we continue with MInChI InChI. Next time, we will continue with the next layer, which is actually the stereochemistry layer. And for that one, André Jerin may join us, who is chairing the group for the enhanced stereochemistry. So all changes from allenes, atrope isomers, whatever have to be entered to InChI will be presented next time. With that, I would like to hand over to Leah.
Great, thanks so much, Gerd. So as Gerd mentioned, MInChI is really an application of InChI. So we're incorporating InChI into MInChI. So we depend on InChI itself. We depend on the work for the stereochemistry, for example. We're hoping progress for organometallics, all of those things. We depend on all of that work within the mixtures use case. So just thinking, this is where we started in the project, really thinking about sort of bench level mixtures. And I know there's other ways to think about mixtures, but we were thinking of things that are not stoichiometric, really, solutions that are made up in the lab, and realizing that, most information tracking systems are really just managing one component, but we need information about other components. We need information about relative ratios between components. So there's really just not a lot of, there's a few places where people have taken the time in their own local data stores to organize information about multi-component system because it matters to them. But for the most part, data around multi-component systems is not organized at all. It's just in this sort of free text form that you see at the top. So we have a double problem here. We have messy data and we have no sort of systematic way of managing it. So that was the use case that we started from. So we really wanted to be able to leverage the strengths of InChI to be able to identify all of the components that we're trying to keep track of in a multi-component system, and see if we could, incorporate those into that succinct line notation motif that InChI has. So InChI is really suitable for this because it does help us exactly keep track of those individual components, and we can link, because InChI is already incorporated into so many great large data sets and data storage places, we can, this will now allow us to connect any local data information we have about multi-component systems into these larger systems. So you can see we have a solution here. On the right side, we need to know, what are the components, what are their relative relationships, And relationships are usually described through concentration and also often through hierarchical relationships. So you have submixtures that are mixed ahead, and these, because the concentration is expressed relative to the submixture, you end up with this hierarchical organization of the relationships between the components. So concentration is a really critical piece of information to keep track of. So basically, what we came up with is an approach to concatenate all of the InChIs of the components, followed by some information about the concentration. So here's a little bit simpler example. So for example, a very standard solution that you're actually going to find probably in a lot of other clinical scenarios, as well as the lab scenario, would be your formaldehyde solution in water, maybe stabilized with some methanol. So you have a couple of different concentrations showing up there. The methanol is stabilized to a range there. How do you manage that? So you have your list of components. That's pretty straightforward. The formaldehyde and water are actually pre-mixed here. So we've grouped the formaldehyde and the water here and added the methanol. And then this layer here, it identifies each of the components. I guess I should explain. So here are your InChIs for each of those components, and then which are ordered according to the standard InChI approach. There's an ordering algorithm in there. So this is now a canonical set of components in and of itself, just this blue part here. And then we use this end layer to keep track of all of these different component numbers. And as I mentioned, there's a submixture here of the formaldehyde and water, and then you add the methanol. And then this key here in the end layer ties to the G layer. And the G layer, I don't know why we came up with G. I think it was the letter that wasn't being used, but this layer is for concentration. So on the next slide, I'll show you what all of these notations mean as far as which type of concentration measurement. But basically, this is encapsulating the relative concentration of the formaldehyde and the methanol that we have here. And so you can see in the curly brackets, this is the concentration of the formaldehyde. There's nothing after the and symbol, which is the connector, because there's no concentration given for water. And then here's the methanol added after hers at the end. So that's essentially how it works. So here's a little bit more about the concentration. And again, this is our formaldehyde solution. You can see the hierarchical nature of it here. So because mixture information is in the messy state that it is, it's reported in a lot of different types of concentration out in the wild. And so at the moment, we're trying to capture a reasonable number of these. We don't always have a lot of data about these solutions to be able to convert a lot of them. I think in the future, it'd be great if we were better managing our mixtures and we could be converting more of these into molarity and other more standard forms. But for the moment, we're trying to capture mixtures as concentration as reported, so that we can keep track of it as is. So this is just our approach for doing that. It's pretty straightforward. It's not that complex. So that's basically how mixtures, the MInChI works. So based on that, that was the early work of the group, was to kind of spec that out. And then from that, we have started building some pilot tools. So we have an open source mixtures editor. It uses a JSON approach to organizing the data from which we can generate the MInChI. So just sort of manages the information coming in from the mol file about the structures that we know, and then all the information about the concentration. This is a little screenshot of our demo tool. I have a link for it later in the slide, so you can go and there's several examples already in the demo where you can add your own components and make up your own mixture and create a little MInChI string from that. So that's just a way to see how it works in practice. So the JSON format that we're currently using to organize this in that open source tool is organized in this way. It's very minimal. It's very simple. It just pulls in the mol file to convert it to the InChI. There you can see we're keeping track of our quantity in units for the concentration. And we're using the hierarchical structure of JSON to keep track of the hierarchical nature of the components. And those are the three basic requirements for MInChI, are those three pieces of information. There's a lot going on in this slide. I just wanted to, these are some of the use cases that have been brought to us over the course of this project, and trying to think about how MInChI can apply to these. Up here in the upper left, you're thinking about solubility of a compound in different solvents. You want to track that at different concentration levels, maybe optimizing other parameters like temperature or whatever. It's really easy to track those series. So that's something that's really handy for MInChI. Keep track of varying concentrations of light components. And that could be a very compelling use case for MInChI, I think, because you have the same set of components, and you're just varying the concentration. And so it'd be very easy to track that data. So once we get MInChI into systems, I think that can be done. I should mention our tool partner is Collaborative Drug Discovery. They had a grant to build these open source tools for the community. And so they have actually incorporated the mix file JSON form into their ELN, actually. So they do have people starting to use this in that ELN scenario. Another place, and this is another early use case that we were looking at, is keeping track of registries and inventories. And in particular, so you can manage hazard information. Again, in a situation with a hazard, the solute might be hazardous, but the solvent actually might be bringing more concern about hazards as flammability, corrosivity, than the actual solute. So even though as chemists, we're thinking more often of the solute in a solution, the solvent actually may be quite relevant for hazard information management. So that's another use case where MInChI could probably really help with that. We've also, down on the lower right here, we've also talked with people who are working with formulations. So right here, you're seeing sort of a dishwashing liquid formulation, but you could imagine any consumer product here, shampoo, cosmetics of some kind. And the interesting thing about these is there's definitely some active components that you can discern the structural information about them, and that's important, right? We're using InChI, we need to have the structural information. That's really helpful. But then there's always natural products that are often added to these formulations. There may be they may be adding different perfumes or dyes, depending, you can get different scents when you go to the store. So there's often a lot of unspecified information. In this case, the natural product, the coconut derivative here, there is a trade database in the cosmetic industry called InChI. You can see InChI there, and they do define natural product sources there. So you could incorporate using this InChI number into your data organization, but it makes it messy because it's not really a definitive structure, right? This is a natural product. It's probably got a lot of different components in there. There's some probably some fatty acids in there, but what else is in there? It's a natural source. It's not going to be consistent. So there's some limitations in what you can do here, but it could still be potentially useful for keeping track of the different components that are involved in that formulation, and also the different processes, because of using the N layer allows you to organize the order. You could also use the hierarchical structure to attach it to data that you have about the process. So if you ran it at a certain temperature while you were formulating it, and then you added something after that. So there's definitely some opportunities potentially for MInChI in data systems that are managing formulation data, but it would have to be in conjunction with a lot of other aspects. And then the last use case that we've talked with the community about is this UVCBs, and this is unknown or variable composition complex products from reactions or biologicals. So these are things that are definitely very complicated, unknown. It's hard to discern. Often there's not much you could say about structure, or if you have a sense of what might be in there, you have to think about an enumerated approach. So for example, in some of these, you can see you have a series of fatty acids, different chain lengths. You could potentially, in that case, for example, use a MInChI approach. MInChI, I think, is provisional right now, but as we're developing that technology for InChI, you could apply the MInChI here potentially to enumerate all of those chains. So that, so it's one of those areas where it's hard to tell how applicable MInChI or InChI generally would be to the UVCB area, but it is a complex area because these tend to be quite toxic. Often this is where they get flagged, is they're toxic in the environment, and so we're trying to learn more about them. And there, I think there's active research now to actually study the chemical components. So as we're learning more about what is included in these UVCBs that we can articulate, I think potentially MInChI could help, but it's pretty complex. Basically, we have, just as our resources, we have published a paper in 2019 that describes the mix file JSON format that I mentioned, that CDD built. And it's just a nice working case of how you can generate MInChI from a data structure like that. So, especially if you're working with JSON files and are familiar with managing your data that way, that's a helpful paper to think about how MInChI can be applied. And we also have a GitHub repository with specification on it, and the code for the open source mixture editor that I mentioned is there, and some there's 30,000 mix files on there that we extracted from text strings into there for people to play with. So it's still in a kind of a test pilot phase, but we have this material. We're hoping people will be interested and might want to play with it. And I think that's it for the slides.